In this video, we'll continue our discussion of higher partial derivatives by working another example out. Notice that we have 3 of these things, but they're mixed partials with x, y, and z. So we got to work our way up to all 4 of those. Okay, so let's do that. I got fx. Luckily, these are polynomials, right? Trig functions with power rules and chain rules would become very gross very quick. But with polynomials, they get shorter as we take more derivatives. Okay, so derivative with respect to x. This first term, y third is a constant, so all I got to deal with is that first one. So it's going to be 16 x to the third, y to the third, plus, okay, that one doesn't even have an x, so it goes away. Okay, I'm going to continue this. I'm working my way up this one. I got fxy. So now I got to take the derivative of this thing with respect to y. 3 comes down times 16 is 48. X to the third is a constant, so it stays that way. All right, we add the next part. Now they want us to take the derivative of that thing with respect to z. Well, there's no z, so that derivative is 0. All right, so we just work our way up each one. So I'm going to write these down. Okay, we should know what this is. This should be a 0, right? Mixed partials should be the same as long as they have the same ones. But let's double check it. Okay, that first underlying term there with respect to y, I got 12 x to the fourth y squared. The second term does have a y in it, so I get 4y z to the third. Now I got to take my derivative with respect to z. The first term doesn't have a z in it, so it's gone. But the second term has a z in it. It becomes 12yz squared. And then we have to take the derivative of that with respect to x. So it actually spits out a 0 like anticipated. All right, we got another one there. We got fz, and then fzy, and then fzyx. So if it has all the same, we should expect that. It should be a 0. So we're going to take, with respect to z, this first term that's underlined at the top is a 0. The second term with respect to z, I got 6y squared z squared. And then we take our derivative of that with respect to y. So that gets me 12y z squared. And then the last derivative with x is 0. So notice we have this, that one, and that one are all the same because they are continuous polynomials. Each partial is a continuous polynomial. And that we have the same letters. Now the last one, notice we have x, xy, and then fxyx. We should not anticipate. It may happen, but we don't want to anticipate that a 0 is going to happen. It could, but we're not guaranteed it with theory. Okay, fx of that, we already did that. I'm just going to go grab it from up top. That's right here. We've also already did fxy. That is 48x cubed y squared. And then if I take one last derivative with respect to x, the 3 comes down. Normally that'd be 150. It was 50, so it's minus 6. So it's 144 x squared y squared. Notice that is not equal to 0. Right? So it's not the same. All right, so those are more mixed partials. I recommend doing it this way every time. Just work your way up it, down a path. Instead of referring back to each one, you'll make less mistakes. I think when I first started doing this, I didn't do it this way. I just found all of the x's, and then I went and found fxy, fxz, fx, x. I did each one that I could do. I think this going straight forward is better, and you'll catch more of those patterns that you can skip over due to theory.